Okay, so I know some of you have taken calculus before, and you already know that just trying to guess the antiderivative by going backwards is not always the best or easiest way to find an antiderivative, find an indefinite integral. And today we're going to learn a technique called substitution. And I want to show you where this comes from. Okay? You all should be familiar with the chain rule. dy dx equals dy du times du dx. I'm sure you've used that a lot. Where u is some function of x. Because it's easier to see this using the Newtonian notation, I'm going to write it in the Newtonian, which is I have some f of g of x, that's f of u, and I want to find the derivative. And the derivative is just the derivative of f at g, but the chain rule says I also have to multiply it by the derivative of g of x. I want to note a kind of a little notational thing here. I could write here du dx is equal to g prime of x. And this would be it's notation, but it kind of makes sense from a derivative point of view. But we also might write it this way. We might say du equals g prime of x dx. Now, you have to be careful when you do this. This is not multiplication, right? I'm not multiplying both sides by dx, because dx is not a real quantity. Sometimes it's called an infinitesimal. But as notation, this will be really useful when we're doing substitution. So, my next step here is I want to integrate both sides of this equation. So I'm going to integrate the derivative of f of g of x. But I'm trying to think of the words here. The fundamental theorem of calculus tells me that the integral of f of g of x derivative is just what? It's just f of g of x. Right? So I set this equal to the integral of f prime of g of x times the derivative of g of x dx. And now I'm going to change my notation a little here. I'm going to substitute for g of x u and for g prime of x dx du. And so I'm going to get f prime of u du. Now this is the substitution formula. Now this is a little abstract. We're going to see some examples so you see how to use it. But the idea is we're going to change from an integration in x to an integration in u. Now we're going to do that because it's going to make life easier. All right? So let me start off by giving a fairly straightforward example. Right? Have an integral of square root of 2x plus 1 dx. And I want to find the antiderivative, the definite integral of this. So using the substitution rule takes a little practice. You have to get a feel for what kind of substitution will help and what kind won't help. But in this case, I'm just going to state that we're going to use u equal 2x plus 1. Okay? Clearly, I'm trying to simplify the expression under the square root sign. So now, I'm going to find the derivative of both sides here. And using this kind of notational thing, I'm going to say du equals what? What's the derivative of 2x with respect to x? Just 2 dx. So since I'm going to need a 2 dx here, I want to write this as 1/2 the integral square root of 2x plus 1 times 2 dx. All right, that's where this is going to come in. And now let me go ahead and do my substitution. 1/2 integral of the square root of u du. Okay, now I have something much easier to deal with, right? Yes?
Sorry, why did you put 1/2 on there?
Because there's no constant here other than 1, right? But I want a 2 in front of the dx to make it look like du. But I can't just stick in a 2 without multiplying by 1/2, right? Let me rephrase that. I can't change this, right?
Yeah.
But multiplying by 1 does not change it. And 1/2 times 2 is 1. So I'm multiplying it by 1. Is that clear? Okay. All right, so this is just the u to the 1/2. And so the antiderivative of u to the 1/2 will be u to the 3/2 over 3/2 plus some constant. Let me simplify that a little. That's 2u to the 3/2 over 3 plus a constant. But I don't really want this in terms of u, right? I want it in terms of x. So I go back to my original substitution, and I say, okay, so this is 2 times 2x plus 1 to the 3/2 over 3 plus a constant. So that's the basic mechanics of doing a substitution. If you feel a little skepticism at this point, you might want to find the derivative of this. Right? That's pretty straightforward. I multiply the whole quantity by 3/2, right? So I have 3/2 times 2 over 2x plus 1 over 3 now to the 1/2. But the chain rule means I have to multiply by the derivative of what's in here. That's just 2. And so what do I get? 3's cancel, the 2's cancel. Oh dear. Oh, I forgot my half. See, I make mistakes, but I can correct them because I'm on a nice whiteboard. Right, 1/2. Okay, so now my derivative times 1/2 comes out to exactly what I want. 2x plus 1 to the 1/2. Chime in if you catch me in a mistake like that. It'll happen up here on the board. Okay. Now might be a good time to note that there's not always one single way to do this, one single right way to do this. So I'm going to repeat that integral using a different substitution. Okay, I'm going to again start off with 2x plus 1 dx. I'm going to do this a little faster this time because you should be catching on by now. Instead, I'm going to say u squared equals 2x plus 1. Now, the purpose in doing that would be to not only get rid of this ugly thing under the square root, but get rid of the square root altogether. So, okay. What I want to do now is I want to, again, find the derivative of both sides. This is the derivative of u is going to be 2u du, and this is going to be 2x, or 2. This is going to be 2. Thank you.
2
dx. Thank you. So this just becomes u du equals dx. All right, I'm going to go ahead and do my substitution. I have square root of 2x plus 1. I plug in u squared, square root of u squared, and dx becomes u du. All right, well this just becomes u again, right? So this is just integral of u squared du, which becomes u cubed over 3 plus a constant. Well, now substituting back is a little trickier here, right? I have to recognize that, you know, u is equal to the square root of 2x plus 1. So this becomes square root of, sorry, not square root. Oh, yeah, becomes square root of 2x plus 1 cubed over 3 plus c, or in a little simpler form, 2x plus 1 to the 3/2 over 3 plus a constant. So we get the same result. You know, I wouldn't say one of these is better, but you'll certainly come up with problems where you'll try a substitution, it's messy, and you just want to give up and start over. Okay. Let's try something that's
Professor?
a little more gutsy. We okay here? Yes.
Can you go back to the problem?
Where's one?
On the part where it's like integral of square root of u squared u du, to the right, yeah. Where did the u go when you changed it to u squared du?
Okay.
So going along the problem.
Okay, so 2x plus 1 is u squared. That gets put here, right? That's square root of u squared u. And dx becomes u du. Right? So this comes in here.
No, but like on the next part, like when you simplify the u squared of u squared.
Well, u squared of u squared is u times
Oh,
u
right. Okay.
is u squared.
Okay.
Okay. All right. Let's do another one. Oh. I want this, but if I use it, I'll have to. I had a blank board here. Yeah. Keep it all as long as possible. All right, example number 2. Integral of x over the square root of 1 minus 4 x squared dx. So take a look at that. What might you think might be a good substitution, nice substitution here? I mean, whenever you see something like this, that's a suggestion, right? Let's go ahead and try that. Let's set u equal to 1 minus 4 x squared. So du equals minus 8x dx. Now we look at that and we see, well, x dx, x dx. That's good, but we've got minus 8 here. So again, maybe we'll rewrite this negative 1/8 integral negative 8x over square root of 1 minus 4 x squared dx. And now let me go ahead and do my substitution. So negative 1/8 negative 8x dx, that's just du. And we substitute in 1 minus 4x squared here, square root of u. Okay, now we have something that is much more palatable. This is just x to the negative 1/2. Right? So, without forgetting about my 1/8 this time, this is just what? X to the negative 1/2 will be, u to the negative 1/2 will be u to the 1/2 all over 1/2 plus a constant, or negative 1/8 I'm always trying to do math in my head while I'm talking, and it doesn't work. This 2 just cancels one of the 4's. U to the 1/2 or square root of u plus a constant. But again, I'm not done here. I still have to substitute back in for u. So this becomes negative 1/4 square root of 1 minus 4x squared plus a constant. Now, this is one way to do this problem. Turns out that when you see an expression like this, 1 minus something times x squared, square root of it, especially in the denominator, but it could be in the numerator too, you might want to think of your trigonometric identities, right? Very specifically, sine squared x plus cosine squared x equals 1. And how's that How's that going to help me here? Well, let me write this back again. Square root of minus 4x squared dx. So if instead I substitute, instead of u equals 1 minus x squared, I'm going to substitute instead x equal to 1/2 the sine of u. Again, I want to find the derivative here. Dx equals 1/2 cosine u du. And the substitution will start to make sense in just a second. Right? All right, I'm going to plug in for x 1/2 sine of u. On the bottom, I have square root of 1 minus 4 times 1/4. So wait a minute. Let me back up here before I put myself into a corner. Leave that off. I should look at my notes before I do these things. Okay, so x dx, right? X is 1/2 sine of u, and dx is 1/2 cosine of u du. And on the bottom, I have 1 minus 4 x squared, which is 1/2 squared cosine squared u. So 1/4 cosine squared u. All right, so now you see the whole point of this. I end up with an expression 1 minus cosine squared u, which if you use this backwards is just what? Just the sine, right? All right, I have these 1/4s, 1/2s to deal with on the top. I'm just going to pull them out. Sine u, cosine u. And now sine squared of sine squared is just sine of u, which very nicely cancels. I just end up with 1/4 cosine of u du, which turns into what? 1/4 sine of u plus a constant. Well, the catch here now is I have to substitute back for x, and I've got sine of u. Like, is that right? Does that work? No, I did something wrong here. Oh, I don't have. Oh. Pause while the professor rethinks his career goals. So x is sine of u. Dx is cosine. Oh. This was sine, should have been sine, and therefore this should have been cosine of u. That should be integral of sine of u. And this should be negative 1/4 cosine of u. Okay. Now we're back on track. The problem here is it's a little bit tricky since we don't have an explicit definition of sine u in terms of x, but we can make one up, right? We start with x equals 1/2 sine of u. We square both sides, giving x squared equals sine squared u over 4, or 4x squared equals sine squared of u. We subtract both sides from 1. And now we find the square root of both sides. Well, this is just 1 minus sine squared is cosine squared of u, so the square root is just cosine of u, and that's equal to the square root of 1 minus 4x squared. So now I can substitute that back in here. I get negative square root of 1 minus 4x squared over 4 plus a constant. All right. It doesn't actually seem like that was a better way to do it, does it? It's a little confusing. But again, the point is, there's often more than one way to do this. And this is the one area of calculus where you really have to be a little creative. And it's going to help if you do all the homework and practice and get some experience. So, yeah, did I see a hand over there? No. Okay. All right. We have a version of this. Let me find some more space here. We have a version of this this is for indefinite integrals. And if you have a definite integral to solve, you can always solve it as an indefinite integral, substitute back, and then plug in your limits. But there is a more direct way to do it. You need to, let's start with the original formula. F prime of g of x times g prime of x dx equals f prime of u du. And if I add limits to this, making it a definite integral, then I can, once I'm done solving for u, I can evaluate it in terms of u, but I have to convert the limits. So I would convert them into g of a and g of d. And that can save some time. I'm doing pretty good on time here. I want to give you one more example because it's a little different. It's actually a little simpler. I guess we could do this one in terms of a definite integral. So let's just let's take the integral from 1 to e of the natural log of x over x dx. So again, we want to do a substitution equals some function of x. And we're going to set that equal to the log of x. So now du is equal to, all right, everyone, I should be real clear. What's the derivative of the log of x? 1 over x, good.
Times
dx. So now this is going to become what? 1 over x x dx, that's du. You kind of 1 over x dx, that's here, becomes du. And log of x is just u. All right, let's convert our limits now. So the log of 1 is 0, and the log of e is 1. Okay, this becomes pretty simple now. This becomes u squared over 2, 0 to 1, or just 1/2. So you can see this can be a very powerful technique. It's one of a number of techniques we're going to learn. Before I leave this, I always like to think about what are we doing here. I mean, I show you this formula, and we do this mechanical thing, but what's the kind of visual explanation for this? And I was just thinking about this before class, and so I wrote it up. And I hope this will help a little, just to give you a feel for what we're doing here. This is one interpretation of what we're doing here. So what I want you to do is look here. I have a function which is just y equals x, or f of x equals x, and I'm integrating it from 0 to 1. It's a real simple problem. If you look geometrically, it's super easy. It's a triangle with side 1 and height and base 1. So obviously the area is just a half. And in this first integral, I'm integrating along the x-axis, and I get a half. Well, an alternative way to look at this is to say I'm integrating along this angle. Now, this is actually a hard problem. We don't even have all the equipment we need to do this yet, so I'm going to have to hand wave a little here. But I know that the base here is 1, and I have to do a little trigonometry here. I have to say, well, I know that r, which is the length from the origin to this segment here, well, I know that r squared is always equal to 1 plus y squared. That's my Pythagorean theorem. And I also know that y over r is the sine of theta, the variable I want to integrate across. So I can combine these two, and I come up with this equation that says r, or r of theta, is equal to 1 over the cosine. Okay? Now here's the part we don't have yet, which is we don't know how to integrate in polar coordinates. That's going to come later in the class. But again, there's a formula. Basically, it's 1/2 1 over that function squared. And so you get 1/2, 1 over 1 cosine squared theta. And I've also changed the limits here. Here my limits were 0 to 1. Here my limits are 0 up to pi over 4. And if you're curious, you can plug this into your calculator and you'll find out that it comes out with the same area. The point of this is one way to look at what we're doing with substitution. We're changing the coordinate system. Now, you wouldn't think that by changing the coordinate system, we'd change the area. And you'd be right. So that's kind of the alternate idea of what we're doing here when we substitute. We're changing our coordinates to ones that are more convenient, unlike my example where they're much less convenient. and trying to simplify the problem. Okay, are any questions on this right now? I have a limited number of worksheets, so the two people who already have them, please don't take them, or we'll run out. So these are some example problems. I don't think we're going to have time to go through all of these, so why don't you just try the first two, and maybe we can finish these up on Thursday. Yeah, why don't you just work on the first two, and when you're done, we'll take a look at those. Okay.
Oh yeah, I do have that.
You done calculus before? Did you get a worksheet, Kimberly? Okay. Someone want to suggest a substitution for number one?
U equals 1 plus x.
Okay. Has anyone tried anything else? Squared equals 1 plus x. Okay. Those both look good to me, actually. I'm not really sure. Take a vote. Number one. Anyone want? Okay. 1, 2, let's take 3, 4. Number two. This is actually what elections are like in the U.S. Hardly anybody votes, but everybody complains afterwards. Okay, we'll try the first one. So u equals 1 plus x, and then du equals x. So this becomes,
We can also write x equal to 1 minus u,
x equals
u minus 1.
u minus 1, that's true. Well, that's going to come in handy, isn't it? Because I've got an x over there. So that's u minus 1. The square root of 1 plus x is square root of u. dx just becomes du. So multiplying out here a little, I get u to the 3/2 minus u to the 1/2. Let's convert these also. So I'm going from 0 to 3 in x,
1 to
going to 1 to 4. All right. Back here. So u to the 3/2 is going to be u to the 5/2 over 5/2 minus u to the 3/2 over 1/2, which is just going to multiply it by 2. I want to go from 1 to 4. All right, so 4 to the 5/2, well, that's the square root of 4, 2 to the 5th, is 32. This 2 is 64 over 5, minus 2u to the 3/2. So again, square root of 2 cubed is 8, times 2 is 16. That's it. And now minus plugging in 1, which is going to be, that's easy, 2/5 minus 2. Okay, so 64 fifths minus 2/5 is just 62 fifths. Minus 16 plus 2 is minus 14, and I guess I should put it all over a common denominator. So 62 minus 70 over 5 is minus 8/5. Anyone get that? Somebody get that? It's going to take a little practice, I guess. Did I forget something in the denominator? Where? Here? So, you agree with this? No? Shall I go back to here?
It's minus 2 u to the 3.5 over 3.
Thank you. Somebody's paying attention. This is 3, right? Isn't that what you're saying? 2/3. And then this is just going to be thirds also? So what happens over here? 14/3? Okay. So 186 minus 70 over 15, 116 over 15. Is that better?
Yeah.
Okay. Now, I'm going to remind everyone that the world has changed. In the past, you just have to look at your calculation carefully, check it. Today, you have a calculator, and it's not a lot of work to say x times the square root of x plus 1. That's my function. And again, reminding everybody, if you hit the second calc button, you say 7. So I want to integrate from 0 to 3. I get 7. Again, this is an approximation, but it certainly looks like that repeats. Okay, so what's 116 divided by 15? Why is that number? Great. you should check your work this way. It's just much, much better than, you know, trying to go through the... Now, if you find out it's wrong, then you need some smart classmate, not during the test, of course, to point out that you forgot the denominator. So, okay. Number 2 is just a definite integral. And I think it's actually a lot less messy. So let's take a look at that. Despite having large numbers, this is actually quite straightforward. That's something you want to do in math, is not let the numbers scare you. I mean, at least not until they justify being, you know, jump out of the blackboard. Okay, so what's the obvious substitution here?
X cubed plus 5.
U equals x cubed plus 5. And whoever wrote this problem is going to reward you as soon as you find its derivative is 3x squared. And you immediately go, aha, look at that. It's going to work out nicely. I do need a 3 here, right? So, again, we'll do that simple trick. So now I'm ready to substitute with abandon. All right, I don't want to forget my 1/3. But 3x squared is now dx is that just becomes my du. This stuff here just becomes du. And x cubed plus 5, that's just u to the 9th. So, okay, that just becomes u to the 10th over 10 times 1/3. And now all I have to do is substitute back. So I get x cubed plus 5 to the 10th over 30 plus my constant. Obviously, you can't check this with a calculator, but it's very easy if you just find its derivative, use the chain rule, you'll see very quickly you get the right answer. All right. I'm not gonna. There's a homework assignment which you should work on, but why don't I add to that? Just do number 3. Do it because it's going to be fun, right? And we'll talk about 3 when we come back on Thursday. I think you probably had enough for today, right? Quiz and all. I'm here if you want to have questions about anything. Have a nice evening.